Okay, Bismillah ar-Rahman ar-Rahim. Salatu wassalam ala ashrafil mursalin Sayyidina Muhammad wa ala alihi wa sahbihi ajma'in. Assalamu alaikum, everyone. First of all, thanks a lot for coming early. So I had to finish early today for something I have to do. First of all, inshallah, we'll try to be 6:15 sharp out of the room. So I'll try to finish even earlier so that you can have time for your questions. Today is the last lecture in this series talking about geometric PD control. Let me start as usual with a recap of what we discussed in the past two lectures. So we're considering now the geometric proportional derivative control on SO3, just as an example for a manifold and how can we do geometric control on such a manifold. And this is not any manifold, so this is really one of the most fundamental manifolds. It's part of SE3, so if you can, it's actually the hard part of SE3. So if you can do control on SO3, SE3 becomes an easier task. So, sometimes it's trivial. If I have some time, I can show you in the end. Sometimes it's more complicated depending on the application. We're going to be looking at both, inshallah. But now we're just considering SO3. So we're having a prototypical example on SO3. So we're talking about here the satellite example given by the kinematic equation and the dynamic equation. The first one is that R dot is equal to R multiplied by the skew-symmetric form of the angular velocity. And the second equation is the momentum balance. And then we cast it into state space form, choosing the states as the rotation or the orientation of the satellite and the angular momentum. And we wrote them in this form. And that's it. So here it's written in this form, emphasizing that we have this map beta R that goes from R3. So omega, the angular velocity, is in R3. And then when it's mapped by beta R, we go to the tangent space of R to SO3. And this map is simply given by R omega tilde. Okay, so it's just a fancy way of writing this map, but we're going to be emphasizing a lot. This map will be crucial today for deriving the geometric proportional part of the controller. We aim to design a geometric PD controller that's given by the sum of two terms, the proportional term and the derivative term. The proportional term that we wanted to come from the gradient of some potential function, and the derivative term we wanted to make the Lyapunov function asymptotically stable so that we can guarantee that this desired equilibrium point is an asymptotically stable for the closed loop system, which is given by this equation. And now, how can we, the question is, how can we formulate or how can we derive this control law in a geometric way such that we respect the non-Euclidean structure of SO3? And then this will be done by having, as I mentioned, so the proportional part as a gradient from some potential function that we choose. So this is the choice that we have. We can choose this potential function as a function of the rotation matrix on SO3 such that it has the minimum, and then it's a valid Lyapunov function. And what sort of options do we have? How can we design this derivative term such that we can inject damping into the system? And this was with the 5 questions that we posed. So if you can solve these 5 sub problems, then you've finished designing the controller. The first one is, how can we design the error function between our desired orientation and the actual one that we have, that we estimate from using some Kalman filter or state estimation algorithm, or we measure directly with some motion capture system. How can we design this Lyapunov, this potential function to be positive definite? How can we compute the gradient or the differential of it, or how, so in the covector that corresponds to the equivalent to the gradient of this function? And then how can we convert this gradient or this differential to a torque in the end? And so this will be the proportional part, and how can we design the derivative part? And this is what we did last time. So the error between R and RD is simply given by RD transpose multiplied by R. So it's the relative orientation between the actual frame, the actual body fixed frame, and the desired body fixed frame. And our goal is that RE, the error rotation, would converge to the identity which means as time goes to infinity, which is equivalent to having that R goes to R desired. The choice that we had for the potential function is given by half transpose of the identity minus RD transpose R. And we've shown last time that it has a minimum at RD at R equal RD. So it's easy to see here when we have RD, when we have R is equal to RD, then RD transpose multiplied by RD is equal to the identity because of the fact that they are it lives in SO3. And then we have that the trace of the identity minus identity is 0. So it's traced. This is straightforward. What was not straightforward is that we need to show that it is positive definite everywhere around for RD, for R not equal to RD. And then we showed last time that we can write this as 1 minus cosine some angle. And we know that the cosine part lives between -1 and 1. So in the end, we can show that the psi of R lives between 0 and 2. So it takes only values from 0 and 2. It only has a 0 at when R is equal to RD. And it can take 2 in other cases, okay? So, and it's between that. And it's an equality, okay? So when theta is equal to 0, we have the cosine is equal to 1, we have the minimum. And we have the maximum when theta is equal to pi over 2, equal to pi. And this is allowable. So we can have the pi, which is 180 degrees away, R and R desired are away from each other by 180 degrees. There are 3 cases when we have the case of theta equal to pi. So imagine that this is our desired frame, and our initial frame, if it starts at the desired frame, so both are exactly the same, then we have that R desired R and R desired are the same, and the error between them is identity. So we have here the fact that psi of R is equal to 0. When you rotate around the x-axis, around the top axis, the Z1, by 180 degrees, okay, then you have that theta is equal to pi. But I can do this around the Z-axis, I can do it around the x-axis, and I can do it around the y-axis. All of these 3 rotation matrices in the end have theta is equal to pi. I'm mentioning them now because they will be important later on, okay? But just keep this in your mind for now. How did we compute the differential of this function that we chose? We said that this is how the differential is defined on any manifold, not just on SO3. This is just an application to SO3. So the differential of any function on a manifold is defined as the unique covector that lives in the tangent space. It lives in the cotangent space at the point R to this manifold. And it's given such that when we pair it with any, okay, so here the red vector is any vector in the tangent space, not in the cotangent space, in the tangent space. We choose any one, so this is arbitrary. When we choose any here, delta R, which is just the name of the vector, so it's arbitrary, and we pair this covector with this vector on the tangent. So, and this is the pairing that is defined of this, it's special for this vector space. We have it's equal to the limit, or you take the differentiation as epsilon for epsilon equal to 0 of psi of RE, and RE here is a special curve that starts at the point R and has at epsilon equal to 0 has this vector that we chose. Okay, the intuition behind this is that we want to know the differential of psi at the point R, so we stay at R, and then we take a small step, okay, in the direction of lambda R, delta R. So this small step, okay, I cannot have it like with a normal plus, so I need to take into account that this is a curve and I need to differentiate that curve. This is the idea. And then we differentiate as this small step tends to 0. This is the whole idea of taking the differentiation. It's very similar to when we say that the velocity is equal to the position now and the position at some instant, okay, just a little bit, and then I take the derivative, I take the difference between them, and I divide by this difference as it tends to 0. The same idea is the same intuition. But here we have a manifold, so I don't have a vector space structure. And last time we showed that when you have a vector space structure, how is this defined, this differential operator? This pairing on the tangent space of SO3 is given by simply the trace. So if you give me any, first of all, vectors that live in this vector space, what dimension, how do we write them as matrices? What dimension do they have? 3 by 3, exactly. The first thing that comes into your mind is R dot, right? So R dot lives in this space, and R dot is a 3 by 3 matrix. So, and any other vector that lives in this tangent space will have, okay, this a 3 by 3 form. What about this covector? What dimension does it have? It's also a 3 by 3 matrix, okay? And then if you give me any delta R, which is a vector in this tangent space, and any covector gamma, for example, how can I combine them to get a real number? How is this pairing defined? It's given simply by the trace of this matrix multiplied by that matrix, and then simply you get a number. Okay? So this is how this pairing is defined on the tangent space to SO3. And then, so this was just the formal definition. And last time we said, okay, now we need to compute. The way we calculate this guy is by simply calculating the right-hand side and calculating the left-hand side, comparing both together such that we extract this from the equation. So this equation is always defined implicitly. So this is an implicit definition of what the codifferential is. And then you have to do it like problem by problem. So the right-hand side is given by this expression, sorry. The right-hand side is given by this expression. When we differentiate using the properties of the trace, we got that it's equivalent to that. And now if we and then when we have the left-hand side is given by this expression, just compare the left-hand side and the right-hand side, you're going to find that if I choose, for both of these to be equal to each other, then this codifferential, this covector, should be equal to minus half RD transpose. And in the end, we have that this is the codifferential. And you see it's clearly here a 3x3 matrix, right? It is a 3x3 matrix. Now so this is the new part now. So all of this is just the recap, and now this is the new part. How can we convert this codifferential into three numbers that in the end will correspond to the torque that we apply to the satellite, the control torque? All of this we did not have when we talked about the PD control on a point mass, right? Because when we had the codifferential of some quadratic function on R3, then this vector, this codifferential was a vector. So we simply had that the codifferential was R3, and we said that our proportional force or our proportional control input is equal to minus Kp multiply or minus the gradient immediately. If you go back when we talked about the point mass, the controller was equal to minus the gradient immediately. The reason is that this gradient lived, in the case of the point mass, it lived in R3, so it's easy that R3 is equal to R3. Here we have, because of the geometric structure, this is a 3x3 matrix, so we need to transform it into three numbers that in the end will correspond to the torque. So this is what we're going to be trying to do. But again, you see now that we're not talking about vectors and matrices, right? We need to look at this geometrically from an abstract point of view. This is, again, continuing with the technical part. So how do we convert this codifferential, which is a covector, it's in the dual space to this tangent space? How can we convert it into a torque, which we know that, okay, that this is just three numbers. And we know, by the way, don't forget that we know that the torque is actually a covector. We write it as three numbers as a row vector, as a column vector, but we know it is a covector in nature. Okay? And the reason, how the process with which we're going to be doing that is the duality. So the duality of linear maps. And I'm going to remind you now with something we discussed in lecture number 4. I'm pretty sure you all forgot about it. So this is just a reminder of what you saw earlier with something that we discussed it abstractly, but here's the application of it. So we say that given any two vector spaces, U and V, if I have a linear map between them, between these two vector spaces, then the dual of this linear map, we call it A star. It goes not from U to V, not from V to U, but from the dual of V to the dual of U. So it goes from V star to U star, and it's defined implicitly by this equation. Okay, so how do we define it? So first, I take an element U, okay, that lives in, so element small u that lives in capital U, which means that I can map it to V through A, right? So when A eats an element from U, it will give us an element in V. And this element in V, which we call A of U, I can map it with any other element in V star, alpha. So we call the element in V star alpha. And this equation, so this pairing is equivalent to first mapping alpha star, where alpha star here lives in V star. I let it be eaten by A star. So A star eats alpha, and then we go to U star. And because this element is in U star, I can map it with the same element that A ate, which is the U, and then I get the same number. So the pairing on both sides are 8. Okay, so this is how the dual of any linear map is defined. So it's very abstract. Now we're going to be using this for the cases that we have. We have three vector spaces that we can look at. And this is the geometric picture that is particular only to SO3, okay, as the manifold we're interested in at the moment. If you give me any three numbers, I know how to transform them to the Lie algebra of SO3, right? What is this map defined? How does it look like? This S, the skew-symmetric form. Give me any three numbers, I can put them in a skew-symmetric matrix. But of course, this is exactly the element. It's an element of the Lie algebra. And then give me any element of the Lie algebra, omega tilde, for example. I can map it to any element in the tangent space to R. How is this map defined? Multiplied from the right or the left? From the left by R. So, and the example that we know is that omega tilde, when I multiply it by R from the left, I get R dot, right? So you see I have omega as an example. By the way, this is just an example. I can do the same for any arbitrary vector. This is omega tilde, R dot. So R dot is given by, so this LR star is given by R dot, R multiplied by omega tilde. And omega tilde is given by S, it's a function S that eats omega. Clear? Everything here is just the dual. Okay? I can, as I define the S, I can define a dual of S. Okay? We're just going to be calling it the same because actually it's also the same skew-symmetric matrix or operation. And I can call the dual of this LR star. This LR star is just the name of the map that it takes an omega tilde and transforms into an R dot, right? And I can define the dual of. And these dual maps are defined simply by these equations. Now, this is the part we're going to be going to the board and write this in details. And then we're going to come back to the slides to show you the result and continuing on the slide, inshallah. So let's go to the board. My board. Black. No, white. Black. No. Okay. Okay. So let me draw again the picture so that we have these maps in mind. So this is TRSO3. This is the dual space of TRSO3. This is SO3, and this is the dual space to SO3. And this is the map S, R3. And then we're going to have R3 star given by the inverse S, or we can call it S star. The map beta that we defined, so you remember we had a map beta that ate omega directly and gave us here. So this is beta R. It ate omega and gave us R dot, right? So you see now, sorry, let's go and we call this map. We call this map LR star, and we call this LR dual. Okay. You see now, remember when we talked about commutative diagrams. So how can we go from here to here? It's very simple. We go from here to here and then from here to here. Then they're defined the same. And if the dual of that would take us from this space to that space is either these two maps or combining them into what we're going to be calling the beta R star. So you see now what we're interested in is converting d psi of R, which lives in this space, and we want to convert it into a torque, okay? Or just let's call the corresponding covector that this comes from, we're going to call it ER. So it's an error in the rotation matrix. So you can imagine that this is precisely the part that we're going to be, well, it's like the proportional term, right? So proportional error. So this ER lives in R3 dual, okay? So the pairings, we need to define them. So we need to know what the pairings are on these vector spaces. Otherwise, we cannot proceed. The pairing between any two elements here, we know how it looks like, right? So the pairing between, let's maybe do it like this. This is the vector that I want. Sorry, this is the covector that we want. And if I can pair it with any element, let's call it delta omega. Yeah, okay, let's call delta omega. I can pair this on R3. So you see, this is a vector that lives here, delta omega, and ER is a covector that lives here. And I want to pair them together. And then if I take two elements from here, so I'm going to take here an element above, which I'm going to call it delta omega tilde. Okay. And I'm going to pair it with ER tilde. And both of these live on the Lie algebra. Remember that the Lie algebra of SO3 is a vector space, right? It's a vector space. So this is a vector in this vector space, and this is a covector in this vector space. Yes. Now let me close the door. Okay. So this is a covector from this space, and this is a vector from that space. Okay. And these two, I'm going to map this one to this one by S. Okay? Which means that this one will be mapped by what? S star. Clear? Okay. And then I can also, because now I have an element in SO3, I can map it to the tangent space to SO3. So this is the small SO3, the algebra. So I can map this to an element. I'm going to call it delta R. And its corresponding dual, this is the one that I'm interested in. Okay. So I'm going to take d of psi of R. Okay. And this is in the tangent space TRS, sorry, TRSO3. So, and this one will be mapped to that one by the LR star. So this one will have to be mapped to this one by LR, the dual, the star on the top. So far, so good? Okay. This is a scalar number. It's equal to this scalar number is equal to that scalar number. When we talk about scalar numbers, do we talk about any coordinates? No, everything is coordinate free. All of these vectors, they depend on the coordinates, but when we write scalar numbers, there is no coordinate, okay, that are involved. So this has to be true always, no matter what we choose. So this pairing, we know it for sure, right? So this pairing you've worked with a lot, right? If I give you a vector and a covector, how can you write them next to each other? Exactly. And this is the thing where it becomes a little bit tricky, okay? And you need to make a choice. When we talk about vectors, we know that we write them as numbers, okay, as a column vector, right? So that's clear. No one makes a mistake in that. But when we talk about covectors, this is where the confusion comes into play. Sometimes we write the covectors as a column vector, and sometimes we can write it as a row vector, okay? If you write it as a row vector, then the pairing between these two such that we get a number will be ER multiplied directly by this matrix. It's clear? But if we write it as a covector, sorry, this is if we write it as a covector. If we write it as a vector, then we use this equation. Sorry. We use this equation. Okay. So these are three numbers, and these are three numbers. I write them, okay, on top of each other, and then I take the transpose of the first one multiplied by the second. Okay. This is just the convention. Okay. We also had the same, we remember when we talked about the differential on R3 itself, right? But we called it differently because we have like the chain rule when we talk about functions. So in order not to make mistakes, we make a clear distinction when we have the co-differential or when we have the gradient and we write it as a column vector. But when we have three numbers without relation to any function, then you have a choice. You can write it as a column vector or a row vector. Let's choose the one that you're used to, which is writing this as a column vector, but remember, it is, okay? It is a covector of nature. So this is the first one. This term, okay, pairing between any two skew-symmetric matrices on SO3 is given by this expression. It's given by half of the trace of ER tilde transpose multiplied by delta omega and skew-symmetric form. Okay. So this is the pairing on SO3. And the pairing here, we know how to calculate it, right? So the pairing here, we know that's equivalent to the trace of D psi of R multiplied by delta R. Okay? And just to make the distinction, you see here, this is the covector, right? We did not have any transpose here. If you write this not with the codifferential, but with the gradient, then you're going to have here the transpose, right? And then you see all of them will have the transpose. Okay, so this is just, it's confusing. Okay, especially if you're a beginner in this, but always ask whether what you're writing is a vector or a covector. Okay. What's even more confusing, and you're going to see this in some of the papers in the literature, is that we know that the transpose of a skew-symmetric matrix is equal to the same matrix, but with a minus sign. So you're going to sometimes find that this has a minus sign on outside. Okay, and this is written without the transpose. So these are all of the small technical details that sometimes cause confusion. So far, so good? Yes. Which one? This one? This one? Delta R, this delta R. So delta R is any arbitrary element in here. You remember what we said about this being any arbitrary element? When we talked about defining the codifferential, we said when we pair this with any arbitrary element, okay, this is how, so when we pair this with any arbitrary element, we know how we can derive the definition of this. So now what we're going to be doing is that if this is any arbitrary element in this vector space, then it must come from an arbitrary element in the algebra that is mapped by this function. And this should come from another arbitrary element, okay, the delta omega, that's mapped through this function. Yes. So now let's take this equation and precisely this comment and move on. So let's take this one. Okay. Let's see if I can copy it. Looks like not, so let's rewrite it again. So this is ER cos delta omega is equal to half the trace of ER omega tilde is equal to trace R delta R. Okay, and now let's use the definitions that we already know. So if you go back here, if given a vector, how can we write it in a skew-symmetric matrix? We know that. And given any skew-symmetric matrix, how can we transform it into an element of this vector space? We know how to do that. Which means that we know that if this is a vector, then this guy will be equal to the skew-symmetric form that you're all used to with the components of these. And that this element will be given by this expression. Right? Clear for everyone? Let's plug in this one here and see what happens. And by the way, we also know that, so this is going from in this direction, right? We also calculated that this guy should be equal to, from our choice of the potential function, we calculated to be minus half R d transpose. So you see now we can plug in all of these expressions here. This one we don't need it at all. Okay, we're just gonna skip it because we know how the skew-symmetric form. But we have these two expressions here. Let's plug in them there. So let me take these two here. So now we're going to be going the other way around. Okay, so this is going from this direction. Now we're going to be going in the other direction. So this I'm going to write it as minus half R d transpose. This guy is R multiplied by delta omega tilde. You all agree? I can equate this to half of the transpose of ER tilde apply by this. What do you see from the right-hand side and the left-hand side? That this guy should be equal to that guy. Is that correct? No, that's not correct. Why? Okay, so we have, okay, sorry, okay. Yeah, okay, so let me write this. This was not a surprise, but okay. Then we have the half here. So these two should be equal to each other, right? No. Okay, that's a surprise. Okay. Okay. So absolutely. So that's correct. This is a rotation matrix, while this is a skew-symmetric matrix. So we cannot equate them to each other. Physically, it doesn't matter. Okay, exactly. They're not in the same space yet. Okay, so there is something that we can show to simplify this a little bit. And this is something on the side. So this is something from linear algebra. So you either know it or maybe if not, something very useful. And it's a property used a lot. So this is just a small, between quotes, lemma, or just a property of matrices for any matrix A that's in R3 by 3. So we're going to be looking at standard linear algebra. We can write it as a symmetric part plus a skew-symmetric part. Has anyone seen this before? No, had nothing to do with the Rodiricus formula. Have you seen this before? No? Okay. The sim A is equal to A plus A transpose divided by 2. Give me any matrix, 3 by 3. I'm going to add it to its transpose divided by 2. I'm going to get a symmetric part. I'm going to get a symmetric matrix. And the skew-symmetric part of A, so this is the definition, is defined as A minus A transpose divided by 2. Now it's trivial to add these two together. You can do it, just eyeball it. Add this to this, you're going to get the original A. So it looks like a simple trick, but actually it's very deep. This is actually a decomposition of the vector space. Okay, so we're decomposing the vector space of 3 by 3 matrices into a symmetric part, okay, and a skew-symmetric part. And so this is one property. Another very important property is that for any symmetric matrix A, these are two different parts. So here A is different. Okay, so here A is just a symmetric matrix, and B, which is skew-symmetric. Okay, both are 3 by 3 matrices. Then we have this very nice property that the trace of A multiplied by B, which is equivalent to the trace of B multiplied by, or the trace of B multiplied by A, is equal to 0. So these are two very important properties that we're going to be using right now. Take the trace of any symmetric matrix and any skew-symmetric matrix, multiply by each other, you should get 0. Okay, this is very easy to prove by yourself. Okay, so again, just choose any matrix or try to write any, try to prove it symbolically, or try to look it up in any textbook. Okay, so this is fundamental property. Now let's take this property and go back here. So this is a matrix that is a 3 by 3 matrix, right? We can write it as a symmetric part plus a skew-symmetric part. So let's write this guy as half trace of symmetric part RD transpose R multiplied by this plus a skew-symmetric part, and I need to take this guy. Then we have the skew-symmetric part of RD transpose R, multiplied by that. This. Okay. Everything is negative. Yes. Yes, there's negative outside. Yes. The trace. Okay. So, okay, there are a lot of brackets. So sim of this part multiplied by this matrix plus skew symmetric of this part multiplied by this matrix. All of them are inside of the trace. The trace is a linear operator. When you have a linear operator of something plus something, is equivalent to the trace of something plus the trace of the other one. So I can write it as minus half trace of the symmetric part of RD transpose R minus half trace the skew symmetric part of RD transpose R multiplied by that guy. So what do you think about this guy? Should be equal to 0 because it's a symmetric matrix multiplied by a skew symmetric matrix inside of the trace. So we use this property that this guy should be equal to 0. And now we can say that this guy is equivalent to, yeah, let's take them, let's make this a plus and this a minus. Then it's equivalent really to that guy here. Just compare both and see whether it's clear or not. Yes? No, we have that the symmetric part of RD transpose is equal to its transpose because it's symmetric. Right? So in conclusion, let me write the conclusion here. So the conclusion, therefore, we have that ER tilde transpose is equal to minus the skew symmetric part of RD transpose R. And we know that the transpose of a skew symmetric matrix is equal to its negative. So this implies that ER tilde is equal to the skew symmetric part of RD transpose R. And consequently, this implies that ER is equal to, so this skew symmetric matrix, I can calculate it from a vector through the S map. So if I have the skew symmetric matrix, how can I convert it back to a vector? The S inverse, right? This S inverse, if I give you a 3 by 3 matrix that's skew symmetric, you take, you take 3 of the components that don't have the minus, and you say this is my vector, right? So this is S inverse multiplied by the skew symmetric part of RD transpose R, which is equivalent to, I can also write this, I can expand this skew symmetric part as half RD transpose R minus R transpose RD. And here I just use the definition we had in the previous slide when we said that the skew symmetric matrix, the skew symmetric part of any matrix B is equal to B minus B transpose divided by 2, right? Or A minus A transpose divided by 2. So this is exactly what I did. I took this matrix minus its transpose divided by 2, and this is the skew symmetric matrix. So now we have an error. So this is 3 numbers that correspond to the difference, okay, between a rotation matrix and a desired rotation matrix and an actual rotation matrix. And how do we now choose the proportional term? Very simply, the proportional term I'm going to be choosing at some matrix, I'm going to choose some proportionals, positive definite gain matrix, multiplied by this ER. And finally, we have our proportional part. Okay. Who saw this before in some paper? No, this part. This part. So you're going to find a lot of names for this. Okay, so this is just a side remark in case you look at, if you see this in papers. Usually people call the map that goes from R3 to SO3, they sometimes call it by the hat map, not the tilde, but as a hat. And then they call the inverse. So they call the inverse of it the V. Okay. So what we called here the S inverse, they call it the V. Okay, VEE. So they sometimes call this VEE. Okay. Here we use the notation S. Here we use the notation S for this guy, and we use the notation S inverse for that, these two. Okay.
Step from S inverse to QRD. What happened there?
See the skew symmetric matrix of any matrix? So it's defined like this. So I just took this matrix, RD transpose R. I subtracted from it its transpose. So the transpose of RD transpose R is R transpose RD. And I divided by 2. Nope. It's a matrix. It's a positive definite matrix. If you do that, then okay, then you've assumed that KP is a diagonal matrix, and the KP in the x direction, the KP in the y direction, the KP in the z direction all have the same number. So this is just a special case of this one. Here, we're allowed to have a positive definite matrix, which means that I can have diagonal terms that do exactly this. I can have different diagonal terms, but I can also have off-diagonal terms, which will couple the x rotation with the y rotation. So if you have a diagonal, this means that if I have an error in the around this axis, for example, a rotation about the z, I'm going to have a torque only in the z. But when you have a coupling term, this means that when you have an error in the z, you're going to get an extra torque in the y or in the x, or and so on. The minus is because we want to have this to be always the minus of the gradient. It's always equal to the minus of the gradient. This is exactly how we also think about potential forces. If you go back to your mechanics, we said that okay, any force, any conservative force comes from a potential energy, and it's equivalent to the minus of the gradient of this potential energy. It's exactly the same concept, but generalized to manifolds. Okay, so this is how this is how we have the proportional term. Is that clear? Okay, so let's. I'm gonna leave that so you can have it later on. Yeah.
So going back to the expression of the skew symmetric
Skew symmetric matrix. Yeah.
Yeah. So you mentioned something about the layman that you stated the other time, so extracting the metric and skew symmetric.
Yes.
But when we're dealing with an element or elements of SO3,
yeah,
does it? I mean, because at the end of the day, subtracting it from each other like that, will it still? I'm sorry, not SO3 of the manifold itself.
Yeah.
Will it still work?
Yeah, because we don't want every element along the way to be an element of SO3. We gave that function an element in SO3, right? So sorry, we have that function psi. Go back. Let me show you. Let's see, where was the conclusion? Okay, so we had the psi of R. So this ate an element in SO3, and it gives us one real number, right? So far, so good. The gradient of it is a covector. So far, so good. We transform this covector into 3 numbers. So far, so good. We define the map. Everything we did along the way is just, again, steps to evaluate that uses the geometric structure of SO3. SO3 is still a manifold that lives inside R3 times 3, right? So it still has a vector space structure, but this vector space structure is on a different field, okay? So we can still add, and sorry, forget about this. So if I embed SO3 into R3 by 3, okay, I can still do some operations with it because it's still a matrix, right? That's, for example, how I do the symmetric part and the skew symmetric part. But I do it only for particular parts. I don't do it for the rotation matrix itself, right? I do it for the RD transpose R. Right? So I did it for the RD transpose R. You see that the RD transpose part comes from here. So it's a covector. The R comes from the map that corresponds to the vector. So you see, it's not that we're playing around with matrices and we're violating anything with SO3 structure. All of these terms came out just precisely because of the structure of SO3. Okay.
Members of the co-tangent field.
This part alone is the covector. The R part, which came from here, came when we took when we evaluated this dual map. Okay, you're gonna go back to the previous notes, and you're gonna find that the R only popped up when you evaluated this map, and so on. So the last thing is that, so this is our proportional term. We're done. We only have one step left, okay? Proving that we need to choose a derivative term. And by doing that, we need to check whether we get what kind of asymptotic stability we get in the end, if we get any. This is our closed loop system. So R dot and P dot are equal to this expression. We already chose how the proportional term should look like. So the proportional term is equal to minus Kp multiplied by the error. And the error was the transformed version of the differential of the map psi that we chose based on this map beta R. And you see clearly here that we have this duality. On top, we have the beta R that takes us from omega to R dot. And on the bottom, we have the dual of it that takes us from the covector in the dual space to that, to a torque that's dual to a omega. So you see all the duality is clear in this equation. What we're going to be doing now is a Lyapunov analysis. This is our Lyapunov function we choose. Okay, it's not that it comes naturally from what we have. So the H of P is the kinetic energy of the system, is half P transpose J inverse P. J inverse P is omega, right? So it's the angular velocity. So this is equivalent to half omega transpose J omega. Okay, so we're just writing in terms of the P. And this is the function that we chose for the control, the potential function, psi of R. Its differential is given by this guy, and the differential of the H is simply by omega transpose, because this is just a quadratic equation. Now let's do time derivative. Okay, so you should be good at that by now. So this is the Lyapunov function. The time derivative of this expression is the time derivative of the first one plus the second one, because we have a sum of two expressions, each in the separate variable. So we have a separation here between the P and the R. The time derivative of this one is given by this expression. The time derivative of this one is given by that expression. Make sense? So we want to evaluate now this term. So we know that the R dot is equivalent to the beta R multiplied by the omega. Everyone agrees? Okay, so this, I just took the equation R from the dynamics R dot and I plugged in here. Then I'm going to have something very cool without even doing any derivation, without looking at like expanding these terms. You remember what we talked about with the duality? When we have something, this is a linear map. So when we have the pairing of something with the linear map eating the omega, I can rewrite it as something with the dual of this linear map on the other guy, and then I have this expression. Go back to the previous slide when we talked about the dual of the A. You're going to find that this is exactly the same expression. Okay. So this is exactly the same expression. And then we know that the beta R star of this guy is what we defined as the AR in a vector format directly. So you see, oh, no, I don't know what's happening. So you see, we jumped immediately from all of these tangent spaces, okay, to everything on R3 in the end. And everything on R3 we're good at. We know how to do. So this guy on R3 looks like this. So dH of P is omega transpose. And the P dot is given by the equation of motion, so the momentum balance with the control law. And this guy is simply omega transpose ER. You see, I have here omega transpose Kp ER and omega transpose ER. So I just combine them in this term. And the first equation, I have omega transpose P tilde omega. I have this expression. And this one, I have omega transpose TD. So I get these three terms in the end. Clear? Easy? This guy, what should it be? Equal? This guy. 0. Why? Because I have a quadratic form with a skew-symmetric matrix in between. I don't need to write it down. If you're doing standard Lyapunov analysis and you write this in components, this is omega 1, omega 2, omega 3. Then you have a skew-symmetric matrix 0, 0, P1 minus P1, P2 minus P2, P3 minus P3. Then you have here omega 1, omega 2, omega 3, and then you multiply, you have a horrible expression. Everything will turn out to be 0. Okay? So this is 0. What about this term? Is it 0? This term is not 0. This term is a pain, actually. So we cannot continue the Lyapunov analysis without removing also this guy. If you go back to what we did on R3, when we looked at the PD control on R3, this term already just disappeared from the equations because we didn't have this Kp and so on. Okay, so we had here Kp and here was a Kp, so it was easily removed. We're going to be doing this with a very simple trick. And this trick is valid. So we can do that. And you can do it in different ways. But this is just the easiest way at this moment. We're going to be defining a new Lyapunov function. I'm not going to tell you what it looks like. It's not interesting. But this Lyapunov function psi bar, this is the psi bar dot. This is the d of psi bar. This is the d of psi bar. And in the end, when I transform this d psi bar, I get the kp multiplied by the error. So you see, compare here the difference between the psi bar and the psi. You're going to find that here we define ER to be directly the differential transformed by the beta R star, while here I just want this to be equal to the kp ER. Okay. So what we're doing here is very similar to this part, that when we calculated the ER, I got it from this expression, and then I multiplied by the kp. Okay. What we want is that the torque is directly equal to minus the gradient of the psi multiplied by or eaten by beta R star. So this is just the modification. Okay. There are different ways that you can even start directly by including the gain inside of the function, okay, and then you can get in the end naturally the torque is equal to the gradient of that. I can show you some stuff later on, okay. But for now, we modified the Lyapunov function, completely valid, and we got this expression in the end written like this, and this is equal to 0 exactly. Okay. So in the end, we're just left with that term. Any ideas on how do you choose the derivative term? Minus kd multiplied by omega. So we choose the derivative term to be minus kd multiplied by omega. I get in the end minus omega transpose kd omega. And we're done. Do we have Lyapunov stability? We have stability, but we don't have asymptotic stability. Why? Because this is still semi-definite, negative semi-definite. How can we proceed? Lassalle's invariance principle. So Lassalle's invariance principle tells us, let's choose this capital, okay, this capital omega to be all of the state space. Let's look at the set R in the state space that has V dot is equal to 0. Sorry, this should be V dot is equal to 0. And the V dot was given by this expression. So if we want this to be equal to 0 and KD is positive definite, then the only solution is that omega is equal to 0. Omega is nothing else than J inverse multiplied by P. So also P is equal to 0. Clear? Then we need to look at inside of R, we need to look at the largest invariant set. The largest invariant set, we call M, will have P dot is equal to 0. Because we want the P is equal to 0 and we don't want to move after we go there. So we need also the time derivative of it to be equal to 0. So we want P dot is equal to 0. P dot is equal to this expression from the equation of motion, from the momentum balance with the control loss. So this is the TP and this is the TD. So omega should be equal to 0 inside of R. So if I'm inside of M, also omega should be equal to 0. I'm still inside of the same set. So this guy goes and this guy goes. I'm left with this expression equal to 0. This is nothing else than, so the beta R was a skew-symmetric matrix, was the dual of the skew-symmetric S, and also the LR. The skew-symmetric matrix, if the vector is 0, the skew-symmetric matrix will be 0. So nothing else will happen. So this term should be equal to 0. And this guy means that I need to have the skew-symmetric part of RD transpose R is equal to 0. The skew-symmetric part, okay, means so RD, R is the RE, so the error in the rotation, and the skew-symmetric part of it is RE minus RE transpose divided by 2 equal to 0. So RE minus RE transpose divided by 2 equal to 0. The divided by 2 doesn't matter. In the end, this is the condition that we have, that RE is equal to RE transpose. How many options do we have? How many equilibrium points does this consist of? We have 4. We have 4 conditions. There are 4 rotation matrices, okay, that when you transpose it, you get the same rotation matrix. Okay? The first one is the identity. Take the identity, transpose it. If RE is equal to the identity and you transpose it, you get the identity matrix, right? Make sense? So the RE equal to the identity means that R is equal to RD, right? So, but there's another case where RE is equal to rotation around the Z by 180 degrees. If you rotate around the Z by 180 degrees, you get this matrix. Let me write it down. So RE equal to RE transpose is satisfied by 4 matrices. Okay, the first one is RE is equal to the identity, right? So I have something that looks like this. So X, Y, and Z. The second one looks like this. So it's 1, 0, 0, 0, negative 1, 0, negative 1. And this one looks like, so this is the X is in the same direction, the Y is negative, and the Z is negative. And the third one looks like this. RE is equal to 0, minus 1, 1, minus 1. And this one looks like, so the Y is in the same direction, the X is negative, and the Z is negative. And the last one is equal to minus 1, minus 1, 1. And we have that the Z is in the same direction, the Y and the X are inverted. So this is this rotation. The first one is this. So the second one is this. This one is I'm rotating around the Y. So I'm doing like this. It's 180 degrees. And this one, okay, I'm rotating around the Z by 180 degrees. Any one of these four will be an equilibrium point for the system. And this is very important. If you initialize the controller, so now we have a controller. So we have the rigid body, and we have the torques, and I have a controller that will take the R and the omega, and will take some R desired, and will make this system, okay, asymptotically stable. We haven't shown that yet. It's the next step. If RdR is one of these four, you're gonna get a torque of 0. So it will not do anything. So this one is what we want. So if I'm already R is equal to R desired, I should get this one. But if RD transpose R is equal to this matrix, means that if this is the desired rotation matrix, and I rotated 180 degrees, and I initialize from here, I don't do anything. Does this remind you of anything? The same exactly for the pendulum. The pendulum, if I have a controller on it, and I start from this configuration, it's an equilibrium point for the system. So I'm not going to be doing anything. Okay. This is, of course, the unforced system. This is for the forced system. I'm going to have this expression. I'm hopefully there will be an assignment or a small homework that you can see this with your own eyes in the simulation. But the conclusion is that I have 4 equilibrium points. So M has 4 points. It has RE1, RE2, RE3, and RE4, RE1 and 0, RE2 and 0, RE3 and 0. And all of these zeros are the momentum. The momentum should be 0. It should not be moving. And RE4 and 0. So this is the set M. You remember what we did last time when we talked about, I think it was the pendulum? What was the trick that we did? To show that M has only the equilibrium. What did we do last time? The equilibrium that we're interested in. We made we looked at a smaller space, not the whole state space, but we looked at a smaller one. And if you go back to the Lyapunov function, we see that the psi at this equilibrium point is equal to 0. Sorry, psi of RE1 is equal to 0. Psi of RE2 and psi of RE3 and psi of RE4 are all equal to 2. Because the angle between theta R and R desired, this theta is pi. You see, I'm rotating around, each one of this is a rotation around one of the axes by 180 degrees. So the theta, which is the angle between R and R desired, is pi. And 1 minus cosine of pi is equal to 2. So this is this term. So simply, if I look at the V, the Lyapunov function, and I try to make the omega set smaller by taking only values that are less than 2, the only equilibrium point I'm going to have is this one, and then I can prove global asymptotic stability. These three equilibrium points are actually, so these 3 points that are removed from the state space are actually equilibrium points of the system, and they are the only equilibrium points. You can show, but this is, again, this is extra stuff. Okay, so this is some stuff that you can find in the literature. I can point you if you're interested, that this control law at these 3 points is actually unstable. So for the closed loop system, I have 4 equilibrium points. 3 of them are unstable, and this one inside of this step, I can show that it's asymptotically stable. So this is equivalent to showing that R is equal to RD, and 0 is actually a globally asymptotically stable equilibrium point, but it's almost globally asymptotically stable. And that's it. Okay. So this is the control law. So if we go back, so now conclusion is R dot is equal to R omega tilde, P dot is equal to P tilde omega plus TP plus TD proportional derivative term. The proportional term is equal to minus KP ER, and the ER is equal to half the skew symmetric term of RD transpose R minus R transpose RD. And then we have that TD is equal to minus KD multiplied by omega. This is the equation. This is the system. This is the control law. And we have that the equilibrium point. So we showed that the equilibrium point for this closed loop system, the equilibrium point of R and P given by RD and 0. This is an almost globally asymptotically stable equilibrium point, provided that I don't start from the conditions where the desired and the R are 180 degrees around any of the axes from each other. Any questions? Slides or one of these? So it should be asymptotically stable. It should be locally positive. It should. So what we did here by excluding the 2 is that now we have that the Lyapunov function, which is given by h of p plus psi of p, psi of r. So here I chose the values of psi of r less than 2. Okay. So I only look at the values of v that has psi of r less than 2. So it's not the whole state space. And the only points I excluded by doing that are these 3 equilibrium points. So in fact, so this region I'm looking at has all of the state space except these 3 equilibrium points. And this is why we call it, it's globally asymptotically stable, which means that if I start anywhere in the state space, I am going to go to the equilibrium point, but except these 3 points. Almost because to really say global asymptotic stability means you don't have any other equilibrium points. So and actually you have only one. Other questions? This one?
So we can say that the TP is related to the rotation, and the TP is related to the velocity like that.
Isn't that exactly what we have when we look at the point mass? When we look at the point mass, so let me write here the point mass just for comparison. So the point mass was psi dot is equal to V, and we had P dot is equal to the what we call the U, and the control law was that the so this was UP plus UD. The UP was equal to minus KP psi minus psi desired, and the UD was equal to minus KD V. So this is R3, and this is SO3. We have exactly the same structure, so I didn't lie, still a PD controller. The complication, okay, of this guy comes only from the fact that we have here a potential function that's on SO3, it's on a manifold. So this is the only complicated part. But other than that, there's another thing that's complicated also. The fact that this closed loop system has 4 equilibrium points this was never here. Because in fact, this is a linear system. And we said before, if you remember, linear systems have only one equilibrium point, which is the origin. Here I have 4 equilibrium points, which is something to do with the geometry of SO3. Yes, thank you. What else? Any more questions?
How can you fix this issue? Like, how can you know that we need to? Okay, I know that we can know that this is the wrong Lyapunov one, but how can you like know the right one? Especially in that case, it was not like that much easy to.
It's not right and wrong. The first Lyapunov function we chose is to get the ER from with this expression. Okay. The second one is just a modified. We multiplied by a scalar. Multiplying a function by some scalar or by some scalar. Does it change the properties of it? So if you take, for example, a quadratic function, you multiply it by 2, what happens to it? It's still quadratic. So nothing changes in terms of the stability. It's just for our stability to be equal to, for this term to be equal to 0. What you're going to find in the literature, an alternative Lyapunov function, that one that we chose. So this is just an alternative. So an alternative Lyapunov function, sorry, an alternative potential function for SO3. So some people also choose the psi. Let me call it something else. So let me call it the capital phi, so that there's no confusion. So sometimes people choose the function that goes from SO3 to R as the following. So phi of R is defined as half the trace of some matrix GP multiplied by I, what did we have? So I think we had I RD, we had I minus RD transpose, right? Identity minus RD R transpose. Yeah. Okay. And with this controller, so you can say that the proportional term is equal to minus beta R of D of this function directly. And you're going to get this is equal to the skew symmetric term of GP multiplied by RD R. Hopefully, yes. Yeah. You see the difference here is that I made the gain inside, and then I got the torque precisely with what I have. This is exactly, if you go back to the linear case. In this case, we choose, if you remember, the potential function of psi to be equal to half psi minus psi d transpose multiplied by Kp. You see the Kp is included inside of the potential function, and then psi minus psi d. The complication that we had is just for simplicity is that here we didn't include the gain inside. And if you want to include it, it has to be with this G matrix. And this is not the same as the K. This is why I didn't want to go this route, because it will just complicate the things a little bit. But this is much more powerful. So this approach is much more powerful because you do get exactly the same analogy with the point mass case. Okay, so that's yeah.
So now the case we have to design the case ourselves.
Yes.
So how are the cases designed?
They have very geometric meaning here. So this Kp, okay, with this torque is simply, so this is truly the rotation along this axis and this axis and that axis. Okay, so they do have a very good meaning. It's not as good as this one. So if you really want my advice, I would suggest this one, because this GP comes from another. Maybe this is I won't. Let's not say it in front of everyone. So maybe you can ask separately. Okay, so that other people don't get scared. Okay, let's stop here. Okay. Interesting. Okay. Okay. So this GP is called the co-stiffness matrix. It's not the stiffness one. Very similar to the idea of a vector and a covector, but this is now a co-stiffness matrix. Okay, just like I have a stiffness matrix. So you're used to the stiffness matrix between this one, and this is known as the co-stiffness matrix. It's given by this expression. It's equal to, I'm not sure I have this in a paper, but I need to go back to it. So it should be a half trace of Kp multiplied by the identity minus the Kp, plus or minus. And this one is, you can go back and forth between them. So this is just the inverse of this expression. So the Kp is rotation around, so the gain around the X, the gain around the Y, the gain around the Z. The JP has something to do with the geometric structure of SO3. This is where it comes from. And then this Lyapunov function, when you take the gradient of it, you truly get a torque. Okay? This one that you find, okay? So this, I started with this one because it's simpler. We didn't start with this the difference between KP and GP and all of that. Also, this one is in a very popular paper. So anyone who worked on, seen any paper on geometric control on quadrotors, if you're interested, you're going to find there is a very, very famous paper by Taolong Li. So it's a 2010 paper. It has 1,300 citations. Okay, it's very popular, and it's really one of the things that if you see any quadrotor that's being able to recover from a flip, it's because of this controller. Okay? There's just a small difference. This is only control on SO3. If we want to do it on the quadrotor, we need also to have a part on SE3. So we need to have a translational part. This is only the rotational part. We also need to take into account that the quadrotor is underactuated. So these are the only two parts that's in the paper of Taolong Li, but this is the main part on SO3. It's exactly the same. Okay? So, and he uses this approach. This one, if you're interested, I can show you to more stuff. We use this when we talk about impedance control. So I'm going to come back later to this part, inshallah. Let's stop now. Okay, so subhanakallah wa bihamdika ashhadu an la ilaha illa anta astaghfiruka wa atubu ilayk.